The year is 1917, the world is in turmoil, with the Great War raging across continents and uncertainty hanging in the air. But in a quiet Berlin study, another kind of battle is unfolding, one that will change the course of science forever. While nations clash on the battlefield, Albert Einstein faces a cosmic dilemma of his own. Amid the chaos, he's wrestling with questions that reach far beyond Earth, questions about the very nature of the universe itself. Einstein has just published his groundbreaking theory of general relativity, a bold new vision of reality. In this universe, gravity isn't just a force, it's the very shape of space and time, curving and warping as planets orbit stars and light bends along invisible paths. But as he works through the math, something unsettling emerges. His equations insist that the universe can't simply remain as it is. It must be expanding outward or collapsing inward, never standing still. This idea flies in the face of everything scientists believe. For centuries, the cosmos was thought to be static, eternal, and unchanging, a comforting, infinite backdrop to human existence. Even Einstein himself clings to this view. Yet, his own calculations are clear. Gravity should pull all matter together, causing the universe to collapse in on itself. The math leaves no room for a peaceful, unchanging cosmos. Imagine the frustration after revolutionizing physics. Einstein finds his theory predicts a universe that shouldn't exist as anyone knows it. The very equations meant to explain reality now threaten to unravel it. Einstein is torn between two impossible choices. Should he abandon the cherished idea of a static universe, or should he doubt the theory that has already reshaped science? Unable to accept a universe in motion, Einstein searches desperately for a solution. He pores over books, scribbles equations and debates with colleagues, determined to find a way out. What he needs is a new force, something subtle, yet powerful, woven into the very fabric of space itself. A cosmic push to counteract gravity's relentless pull. This isn't something he observes in nature, but a theoretical patch, a mathematical fix designed to save the idea of a static universe from collapse. Surrounded by swirling papers and endless calculations, Einstein invents a new concept. A cosmic repulsion, a force that balances the universe and keeps it from falling in on itself. This is not a discovery born from observation, but an invention born from necessity. A way to preserve a cherished belief in a tranquil, eternal cosmos. The stage is set for one of science's most famous mistakes, a moment that will echo through the history of physics. The universe, it turns out, is far stranger, more dynamic, and more mysterious than anyone had ever imagined. Einstein's struggle marks not just a personal crisis, but the beginning of a revolution in our understanding of the cosmos, a journey into the unknown that continues to this day. To hold the universe still, Einstein adds the cosmological constant, lambda, to his equations. He's searching for a way to make the math match his belief in a calm, unchanging cosmos, a universe that neither collapses nor expands. This term acts as a repulsive force, a gentle push built into the vacuum of space, countering gravity's pull. It's like a cosmic tug-of-war, with gravity trying to pull everything together and lambda pushing back, keeping the universe in perfect balance. It's a clever, if artificial, solution. Empty space isn't empty, but filled with hidden energy. This invisible energy, imagined by Einstein, is woven into the very fabric of the cosmos, quietly shaping its fate. With lambda, Einstein's universe is static and eternal, on paper at least. The equations now describe a cosmos that never changes, a universe frozen in time, just as Einstein hoped. Yet, the fix feels contrived, even to Einstein. It mars the elegance of his theory. The beauty of his original equations is lost, replaced by something that feels forced and unnatural. He introduces it not from evidence but to fit a preconceived idea. It's a patch, a workaround, not a discovery born from observation. The universe, however, doesn't care about our preferences. It follows its own rules, indifferent to human hopes or mathematical convenience. Soon, evidence will show the cosmos is anything but static. Observations will reveal a universe in motion, galaxies racing away from each other in all directions. The real story is written not in equations, but in the light from distant galaxies. These faint signals carry the truth of cosmic expansion across the vastness of space and time. Einstein's patch will soon be exposed as unnecessary, leading to a legendary moment of scientific humility. He will famously call lambda his biggest blunder, a rare admission from a scientific giant. The universe is about to reveal its true dynamic nature, an ever-changing, expanding cosmos, far more wondrous than anyone had imagined. While Einstein tries to keep the universe still, wrestling with equations late into the night, he's haunted by the possibility that something fundamental is missing from his theory. Meanwhile, across the ocean, Edwin Hubble is peering through the world's most powerful telescope at Mount Wilson Observatory, searching for answers in the night sky. Hubble discovers that the faint, mysterious nebulae dotting the sky are actually distant galaxies, billions of them, each filled with countless stars. Even more astonishing, their light is redshifted. Nearly all are moving away from us, as if the universe itself is breathing and expanding. The farther a galaxy is, the faster it recedes, revealing a cosmic pattern that no one had expected. Space itself is stretching, carrying galaxies apart like raisins in a rising loaf of bread, a simple analogy for a profound truth. The universe isn't static, it's expanding in all directions, growing larger with every passing moment. This is the proof Einstein's equations predicted but he tried to erase, doubting the wild implications of his own mathematics. When Einstein learns of Hubble's discovery, he's stunned, realizing his mistake and the missed opportunity to foresee this cosmic truth. The cosmological constant was unnecessary. The universe isn't collapsing, it's expanding, and the equations work without it. Einstein famously calls lambda his biggest blunder, a rare admission from a scientific giant. He missed the chance to predict one of the greatest discoveries of the 20th century, a universe that is alive, changing, and full of surprises. The cosmos is dynamic, evolving, and far grander than anyone imagined, with mysteries still waiting to be uncovered. The static universe is dead. A new era of cosmic discovery begins, inspiring generations of astronomers to look deeper. The universe's true nature is revealed not by theory alone, but by looking up and daring to question what we see. The story of cosmic expansion has only just begun, and the next chapter is waiting to be written among the stars. For decades, Einstein's cosmological constant is dismissed as a cautionary tale. The universe is expanding, gravity is slowing it down, and the fate of everything depends on cosmic density. Astronomers tally stars and dark matter, trying to predict whether the universe will collapse or expand forever. Lambda is forgotten, a ghost in the equations, but the universe has surprises in store. In the 1990s, astronomers used distant supernovae as standard candles to measure cosmic expansion. They expect to find the universe slowing down. Instead, the data is shocking. Distant supernovae are dimmer than expected, farther away than predicted. The only explanation? The expansion isn't slowing, it's speeding up. The blunder returns, not as a mistake, but as a clue to a deeper cosmic truth. The universe is accelerating, and the story of Lambda is far from over. The discovery of cosmic acceleration stuns the scientific world. Two rival teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, confirm the result. The universe's expansion is speeding up. They check and recheck their data, but the conclusion is inescapable. Something is pushing the cosmos apart, a force like Einstein's lambda. Suddenly, the blunder looks prophetic. This mysterious energy, now called dark energy, dominates the universe. Perlmutter, Schmidt, and Rees win the Nobel Prize for revealing a new cosmic force. What began as a mathematical trick is now a real phenomenon shaping our fate. Dark energy is invisible, but its effects are everywhere. Einstein's intuition was right, even if his reasoning was wrong. To grasp cosmic acceleration, we must rethink gravity. General relativity allows for a repulsive force, negative pressure in the vacuum of space. Dark energy acts like a cosmic anti-gravity, a constant push everywhere in the universe. Early on, gravity's pull dominated, but as the universe expanded, matter thinned out. Dark energy's density stays constant, so its influence grows as space expands. About 5 billion years ago, dark energy overtook gravity, and expansion began to accelerate. Now atoms and stars make up just 5% of the universe. Dark matter is 25%, but a staggering 70% is dark energy. We live in a universe ruled by a force we barely understand. Einstein's blunder is now the main character in the cosmic story. The universe's fate is shaped by this mysterious energy. Our cosmic inventory has changed forever. The discovery rewrites our place in the cosmos. what is dark energy? The truth is, we don't know. The simplest idea, it's the energy of empty space. Einstein's cosmological constant. Quantum theory says the vacuum teems with virtual particles, giving it energy. But calculations predict far too much. 120 orders of magnitude more than observed. This cosmological constant problem is the worst prediction in physics. Maybe some unknown law cancels most of the vacuum energy, leaving just enough to drive cosmic acceleration. Some propose a changing energy field, quintessence. But so far, evidence points to a true constant. Dark energy is a ghost in the cosmic machine, smooth and persistent. We know it shapes the universe, but its nature remains a mystery. The greatest discovery of modern cosmology is also its greatest puzzle. Dark energy doesn't just shape our past, it dictates our future. If it remains constant, the universe will expand ever faster, growing colder and emptier. Galaxies will vanish beyond our cosmic horizon, their light lost forever. Future astronomers may see only a lonely Milky Way, unaware of the vast cosmos that once was. The evidence of the Big Bang and cosmic expansion will fade from view. The universe will become a dark, isolated place, a cosmic Big Freeze. Our era is special. We can still see the universe's history before it disappears. The accelerating expansion is erasing the story of our origins. We are witnesses to a fleeting cosmic spectacle. The universe's ultimate fate is one of silence and solitude. The story of the cosmological constant is a lesson in scientific humility. Even Einstein, a genius, was shaped by the assumptions of his time. His blunder was an idea ahead of its era, wrong in motivation, right in intuition. Science advances by questioning, correcting, and sometimes embracing mistakes. The ghost Einstein tried to banish became the key to understanding the universe. In science, no idea is ever truly dead. Discarded concepts can spark revolutions. The universe is cleverer than we are, always full of surprises. Einstein's error became a prophecy, revealing a cosmos stranger than he imagined. Our mistakes can be brilliant, pushing us toward deeper truths. The story of Lambda is a beautiful reminder. The cosmos is always more mysterious than we think.